We're going to quickly go over some properties of covalent bonds, and we're going to go over how we put together a Lewis structure based on the covalent bonds that are formed. Covalent bonds involve the sharing of electrons. However, when we dig deeper into the reasons why covalent bonds form, there are some factors that are coming into play with the formation of a covalent bond. The electrons of both atoms are attracted to both nuclei. But there's also some repulsion between the electrons with each other in the electron clouds. The electron clouds are actually overlapping. The orbitals are overlapping in a constructive way. However, the covalent bond needs to overcome two repulsive forces. The electrons not wanting to be next to each other from both atoms, and the nuclei also pushing against each other. So there's various factors that we have to take into consideration. This diagram summarizes the formation of a covalent bond based on the distance between the two atoms that are overlapping the orbitals. If the atoms are too close together, they cause the potential energy of the system to be incredibly high. You have two positive charges that are very close to each other, and that is very energetically unfavorable. On the flip side, if the atoms are too far away from each other, they're not going to experience any reduction in potential energy. They're actually going to have zero potential energy if they're infinitely far away from each other. There exists a certain distance between those atoms where the overlap of the orbitals does enough to lower the potential energy to make it energetically favorable for those atoms to be covalently bound. They get too close, they're going to repel in terms of their nuclei, but if they're too far away, then there's no constructive overlap of those orbitals. When we form covalent bonds, polarity is a property of the electronegativity difference between the two atoms that are bound. If the two atoms are exactly the same, like two atoms of fluorine, I would expect those electrons to be pulled equally by those two atoms. However, hydrogen and fluorine have enough of an electronegativity difference where fluorine is going to have most of the electron density around it compared to the hydrogen atom. This is a polar bond. We say that it's a dipole. There's two ways that we represent using symbols a dipole. We either use this arrow with the positive side of the arrow showing the more electropositive elements, and the arrow points towards the negative element. We can also use these lowercase delta symbols to show this side of the molecule is more positive, this side of the molecule is more negative. A bond dipole is a chemical bond where the electrons are shared unequally due to the distance in electronegativity. This dipole moment equation is irrelevant in terms of what we need to know for AP chemistry, but it's a value that can be calculated based on the overall charge at one end of the molecule compared to another one. The greater the difference in the electronegativity, the more polar the bond. You can see that HI doesn't have a very strong dipole moment because the electronegativity difference between hydrogen and iodine is not very big. However, you can see with HF that the electronegativity difference is very high, which therefore causes one of the atoms to have more electron density than the other for longer periods of time. We draw very simple pictures of molecules to represent the orientations of electrons around the atoms. A Lewis structure uses symbols of the elements as substitutions for atoms. Single lines represent individual covalent bonds, and each single line corresponds to 2 electrons. Remember that most elements do form chemical bonds to follow the octet rule. Hydrogen is a unique element that follows its own rule called the Duet Rule. So hydrogen is always stable with 2 outer shell electrons because it achieves a helium-like noble gas configuration. 2 atoms of nitrogen bonded together. You put 2 of them together. Each nitrogen atom has 5 valence electrons. But you can see that each of the atoms, if it shares 3 pairs of electrons, will form a triple bond. You can form up to a triple bond between 2 atoms. But you can see that both of these atoms, if they share this pair, and this pair, this nitrogen atom has 1, 2, 3, 4, 5, 6, 7, 8 electrons, and so does this one. Multiple bonds are stronger. They have more energy. We're going to quickly review how we draw a Lewis structure. We're going to follow these steps here. I'm going to break down each one of these steps as we put together this molecule of PCl3. First step, count your number of valence electrons. Phosphorus has 5. Each of these chlorines has 7. That gives me 26 total electrons. Second step is take 2 electrons and make your skeletal structure. Each time I'm adding electrons, I'm taking them away from my total. So that gets me down to 20 because I took 6 away from my total. Next step is let's complete the octets of each one of these chlorines because each one of these chlorines already has 2 electrons. So I'm going to put 1, 2, 3, 4, 5, 6 more around each. 6 times 3 is 18. I'm down to 2 electrons. You always complete the octets of your outer shell or your outer peripheral atoms first. Then, if necessary, those last 2 electrons would simply go on the phosphorus atom. If you have extra electrons at the end, that's when you place them in the middle. If necessary, we can also make multiple bonds, such as in with this Lewis structure, HCN. Same process, I count my number of valence electrons, 10, HCN, 1, 2 electrons, 1, 2 electrons to connect each side, I'm down to 6. The hydrogen is stable. The nitrogen gets all of the remaining electrons, but the red flag that should be going up is this carbon only has 4 electrons. This is a bad Lewis structure because my carbon atom should have at the very least 8 electrons. So to fix that, I can actually move pairs of electrons to form multiple bonds, and that's exactly what I'm going to do with my nitrogen atom to form a triple bond. So this triple bond on this side of the molecule would be higher energy. It would take more energy to break this bond, but it would also have a shorter bond length. This would be a longer covalent bond. That would be my final Lewis structure. We're going to take some time and review some more advanced concepts with covalent bonding in the next mini lecture.